the ascent and eruption of magma on the terrestrial planets, a planetary perspective on the moon. Jim.
Thank you very much. So today, I'd like to summarize some of the work that Lionel and Wilson and I have been doing for the last couple of decades, trying to understand the ascent and eruption of magma on planetary bodies throughout the inner solar system primarily, and then think about how this has implications for the moon. And again, as Brent, picking up on what Brent was saying and also what David, the question he asked, where do we go on the moon to really understand the characteristics of a body which is dominated by dike emplacement, as Brent was pointing out, which is a really critical, important part of the whole process to study. And so we have not only some important information here about the kind of things we can look for on the moon, but also exploration strategies for trying to solve some significant scientific problems. So we've really been lucky in the last few decades to be able to, in fact, do analysis on the Earth and terrestrial planets. And this really provides a huge amount of information about the geological history, of course, and the thermal evolution of each body. So what we've been able to do is to take a look at a synthesis of the array of extrusive volcanic features and landforms. And then this provides insight back into what's going on in the interior, the distribution, the age, the characteristics, and so on. And so, for example, we can look at the size of the planet, we can look at the density of the planet, presence or absence of an atmosphere. All of these have huge impacts on the volcanic style, et cetera, and then, of course, the position in the solar system and incident solar radiation, plus where they formed and what their initial composition is. So a critical part of this is we know from remote sensing measurements and return samples that a significant part of the, in fact, composition of planetary crust has to do with essentially mafic to ultramafic melts. So that's what we'll focus on today, basaltic volcanism. So what are the major styles, if you will? What are the controls on the types of surface volcanic features and accumulations? I'm going to run through just a few frames of reference here. Clearly, magma composition and volatile content, which we'll come back to in a couple of minutes, are critical. But generally, we're talking about basaltic volcanism. A critical thing is lithospheric continuity and thickness and tectonic regimes. Let me go to another slide and come back to this one. When we think about lithospheric continuity, okay, we know that the smaller terrestrial planets, those 1/2 the size of the Earth and Venus, in fact, cool quickly early on. They formed crusts which are dominated by impact cratering, et cetera. They had their major mode of lithospheric heat loss being conduction, okay, as opposed to plate recycling in the Earth and, say, advective heat loss on Io, for example. And this resulted, in fact, in planetary resurfacing, which is dominantly in the early history of the planet, because basically global stress regimes characterized by net horizontal extension, as the planet was heating up initially from essentially radioactive decay, turned to net contraction, which inhibited essentially the ascent and eruption of magma for the smaller terrestrial planetary bodies, the one-plate planets. So this is really an interesting insight into how volcanism is likely to occur on these. Of course, other aspects are crustal origins and stability. If we look at Ross-Taylor's diagram, here we have primary crust generated from the impact energy, et cetera, secondary crust from partial melting of the mantle, and then tertiary crust from recycling of primary and secondary crusts, okay? So this is really important, plus the crustal thicknesses and their density contrast. Mantle thickness is also really important because you need to get essentially a scale length of convection that'll have different outcomes as a function of different essentially mantle thicknesses. It'll control mantle convective style. So these are all really critically important. We know a lot based on what we've seen in the terrestrial planets. So preferred locations for magma reservoirs are really essentially at depth within a planetary interior, for example, partial melting within the planetary interior, mantle plumes in the case of the Earth's seafloor spreading. And we also see relatively shallow magma reservoirs within a volcanic edifice. This is a classic diagram of what a volcano looks like. It's totally wrong. We won't have time to go into this at the present time. It's for the nomenclature, it gets you an idea of what's going on where, but in general, they don't typically look like this. Typically, the reservoirs are in the upper part of the volcano itself, more or less. So let's just take this as a basic concept for deep and shallow reservoirs. Now, magma reservoir formation, the deeper reservoirs, they can form at rheological boundaries. They typically can form and also stop there. And so with increasing rheological boundary evolution, thermal evolution of the planet, they deepen with time, particularly for the small one-plate planets. They can also occur due to pressure release melting at plumes, such as the kinds of things you see, for example, in the major shield volcanoes on the Tharsis region of Mars, and at vertical discontinuities where, for example, you would have essentially density barriers like the North Acidic crust compared to the mantle on the moon. Now, evidence for these reservoirs in these edifices, as you can see here on Mars and Olympus Mons, clearly come from the presence of calderas. So we want to look for calderas as evidence for these on the terrestrial planets. Deeper magma reservoirs have different manifestations. Sometimes you get radial dike swarms. We see these on Mars. We see these on Venus big time. And the position of ascending mantle flow is often seen dynamically, if you will, or dramatically, in broad rises, topographic rise here, such as the Beta Regio region on Venus, the Tharsis region on Mars, etc. Okay, so we not only see these broad rises, they're both constructional and thermal, and they have volcanoes associated with them. So these are good signals as well. Shallow magma reservoirs, okay, commonly form within volcanic edifices. And to build a volcanic edifice and a reservoir requires a lot of magma coming up over a longer period of time. So you need repeated multiple pulses of magma to rise frequently within a spatially restricted region over an extended period of time. You just need to keep supplying this thing so it creates a reservoir. Not a trivial thing to do. On the moon, in contrast, we see low eruption frequencies and great flow lengths, ensuring that typical large edifices will not form. So we really don't see any evidence for calderas as we know them on the Earth, or shield volcanoes, really on the broad, in the classical sense, on the moon. So shallow reservoirs form within edifices at levels of neutral buoyancy, repeated kinds of things like the things we see here, and the calderas, of course, typically result from collapse of the magma reservoir due to flank eruptions. So these are the kind of things we can look for in the planets, and when we do, we see this cornucopia of really interesting volcanic edifices of a variety of types here, but not all these occur on all the planets, and this is the key. From looking at these things, we can really tell what's going on with the characteristics of these and back out a lot of information on the thermal evolution, the internal structure of the planet as a whole. So we know the Earth, okay? Plate recycling, we have a great scale length of convection, so we see these mantle plumes, which have a huge effect on things, and the divergent and convergent plate boundaries create hugely interesting and very well-known environments for essentially basaltic and more evolved volcanism. So we kind of have a frame of reference for this. We go to the moon, it's an entirely different picture, okay? You have primary crustal formation from the anorthositic, forming the anorthositic crust, secondary crust formation with mare volcanism by partial melting of the mantle, and then we have neutral buoyancy zones, potentially at the base of the crust and even at rheological boundaries as the moon's evolving. And we see, in fact, over time, as the lithosphere, as the planet cools, much more efficiently on a one-plate planet, we in fact see coolage, shrinkage, and inhibition of eruption with time. That's why they're fewer as a function of time, and ultimately it dies out about 1 billion years ago. We also see some near-side, far-side differences, which can be logically and reasonably attributed to crustal thickness variations. So for the moon, it's primarily an orthositic crust, one-plate planet, cools rapidly, deep magma sources in the latter stages, etc. And we see no evidence for large shield volcanoes like we see in the Tharsis region, or big calderas like we see associated with volcanoes on a number of the terrestrial planets, Venus, Mars, and the Earth. So in fact, if we take a look at other planetary bodies like Mercury, what kind of array of volcanic features do we see there? Well, there's not much of an array. One thing we discovered, in fact, when we went into orbit around Mercury was a huge area looking straight down on the North Pole of Mercury here. Each red thing indicates a crater. This area here is 6% of the planet, which is formed of volcanic plains. And in fact, the equivalent is this on the moon, shown in yellow, and this in North America. Kind of from sea to shining sea, you have a sea of lava. And so what is the nature of the mode of emplacement of the northern plains? There are no shield volcanoes that we see on the surface of Mercury. We don't see sinuous rills. We don't see a lot of small types of features. There's maybe some suspects, but nothing really equivalent. There are these large, incredibly distributed diffusive volcanism. We cannot see differences in the crater size frequency distribution at a statistical level within that 6% of the surface. That's really amazing. That's a lot of lava coming out over a short period of time. Well, one of the keys might be, in fact, the scale length of the mantle. Mercury is characterized by a relatively thin mantle compared to Venus, Earth, Mars, etc. And in fact, when we take a look at those, we think of thick mantle on the Earth as convecting plumes, big scale length, large scale plumes, etc., basal melting of the lithosphere and production of the Hawaiian Emperor seamount chain, etc. And we see lots of significant edifice building types of things and small flows with narrow dikes, etc., with repeated eruptions. On the other hand, with Mercury, we have thin mantle, convection is inhibited, and we in fact see a different style of convection, which isn't long scale length convection, but rather is broad convection. Not only that, you're heating up the substrate, so you're stressing in extension the lithosphere. So when the lithosphere opens up by this essentially global planetary stress early in the history In fact, the dike width can be huge, which means that the volumes of lava that are coming out over a period of time essentially can be extremely large. And instead of producing little edifices and shields here and there, etc., you produce essentially a bathtub effect. Okay, so this is the hydrostatic flooding mode. It just envelops all the topography you can see and doesn't produce very many landforms at all, other than paving parts of the planet, like we see in this case here. So what about primary crustal formation? Is that on an anorthositic crust? Well, our messenger data, in fact, says that there is no anorthositic crust. So instead of having a flotation crust, surely Mercury has a primary crust due to accretional energy, but it's very much more mafic in character than the moon's. So in fact, we don't have a buoyant crust sitting there that has, in fact, the same kind of characteristics as the lunar crust does. And so that means that the distinction between primary and secondary crust is, in fact, obscured, basically. It's confused, if you will. I mean, we'll sort it out, but essentially you're getting partial melting of the mantle that's coming up not as a flotation crust, but as lava flows, etc. So this means we're going to have a different kind of characteristic evolution of the early history as well. So that's really fascinating, and it gets back to why the moon is so important, because the moon provides, with this barrier, density barrier and evolution, really fundamental information about the nature of dike emplacement on these planetary bodies. So this is one of the reasons that the moon is so important, and it's a critical laboratory for human and robotic exploration to study these kinds of things. Well, how can the diversity of features that we do see be explained? See, I took care of NSA by calling it a cone. This is the ISIS, okay? But you can see there is an array of these types of features here. It's not like the moon doesn't have any of these things, okay? And they range from things that are small and around a vent to intrusive-like things like floor-fractured craters, which Lauren Joswiak will talk about in a few minutes, to huge outpourings like Mare-Imbrium flows up to 1,200 or so kilometers, and then sinuous rills, which are incredible. Turbulent eruption that occur over a very short period of time, and in fact, create these types of features. So these two are huge, these are smaller. How do these things form? So we can account for these really by spectrum of overpressurization and dike emplacement events. So here we have the features, here we have the basic structure, and here we have the shallow crustal structure. So a lot of dikes will be propagated from the mantle and will die a heat death in the crust. A critical question is, where are they, how many are they, and what does that mean? Secondly, shallow crustal intrusion, ones that don't get to the surface, still have gas in their upper parts. They will degas to create crater change, which we see abundant evidence of. These things will actually carry with them mantled xenoliths, potentially, and wall rock that is ripped by the ascent of the dike. So this is the place to go to study, in fact, mantled xenoliths, Davy crater chain, Mendeleev, etc., many, many others, to try to understand, in fact, what's going on in the interior, okay? Not only that, as you get closer to the surface, you'll see the near-surface stress field creates extensional stress, and you create graben, along which the degassing and some volcanism can occur. I think this is exactly what Brent was looking at in our discussions earlier, as he described. And this is really critical, too, because you see the first stages of gas exsolution and how it's manifested. This will also bring up xenoliths, and they're not swamped by later flows. So those blocks you showed on ISIS could be, in fact, xenoliths. So we can see small shield volcanoes, and then we see, in fact, intrusions in floor-fractured craters, which you'll hear about in a few minutes, which are really important because they're also degassing to produce some exciting features. And then finally here, you see the major flows, these huge major dike widths, which in fact propagate these to the surface and not only form these long lava flows, but if the duration of the lava flow is sufficiently long, it'll create a sinuous rill, and details of that are presently much more well understood. So what does this mean in terms of what we do explore? Okay, so here is the list of things that I started to put down. This is 90 seconds. I knew this, so I said this will be treated, this is treated in detail in the paper, okay? Okay, but this is a lot of really good stuff. I mean, there's tons of things to do with these, and I just point out a few, like xenoliths here, like dike widths, geophysical studies, types of analyses that we can do in situ with human exploration and robotic exploration and partnerships of those. There's dozens of studies ranging from the origin of the young Mare basalts all the way back through to, in fact, in planetary bodies, how dikes of this diameter, this width are in fact in place. A critical question. So we have lots of things to do, lots of future exploration. We're doing, in fact, design reference missions for many of these problems, okay? And I just remind you, for those of you in the audience who, like Brent, were not born at the time of Apollo, perhaps, that, in fact, 40 years ago, we've had robotic sample return missions by the Soviet Union, robotic rovers by the Soviet Union, and human exploration, precursors to the surface with Surveyor and other spacecraft, visiting those with humans, that's the lunar module in the background, and then real geological exploration of the moon. Can we do it? We did it. Can we do it again? Of course we can, and it's up to you all to make this a reality. The moon's a great lab for the study of dike emplacement and planetary crust. Thank you very much.
So I think I used the word illustrious and wise when I introduced him, and he's still enthusiastic. Just incredible. Okay, so one brief question. Anybody out there? You're just overwhelmed? Yes, Bill Botke. Go to the microphone because we have people online. Right here or there.
You can take this one, Bill.
You know, you sort of give a quick tour of the terrestrial planets, but one event that you missed was Venus and the possible global resurfacing. Can you make a comment on that in reference to now what we've learned from the Moon and Mars and Mercury?
Sure. I didn't have enough time to get all the terrestrial. You'll notice I didn't say much about Mars either. But so Venus is really critically important. As you well know, there's evidence that it was globally resurfaced in the last 10% of its history. And so how that worked, okay, so there's several theories about the formation of this resurfacing event and its rates, and all of them are really critically important. I just make one statement, which is we really don't know how and when plate tectonics started on our own home planet, okay, on the Earth. A resurfacing event due to global vertical crustal accretion, which eventually becomes unstable, is a good way to do that with a foundering of the crust and initiation of plate tectonics. So I would say Venus, volcanologically, is a really great place to study, potentially, the advent of plate tectonics. Not only that, Venus is going to, the Earth is someday going to be like Venus as it runs down its heat engine, so to speak, and becomes a one-plate planet. It's still going to be volcanologically active like crazy, but it's not going to be at plate boundaries anymore. So Venus is a good example. So for those two reasons, I would approve a discovery mission to Venus in the next round.